So welcome to our final lecture on Chapter 18, Voltaic Cells. We've looked at cell potentials and reduction potentials and figured out which way reactions are going, and then we've used the Nernst equation to figure out what the potential of the cell is as conditions change. Which brings us to what other things can we do with voltaic cell. Given the following reaction under standard conditions has an equilibrium constant of 1.6 times 10 to the 14th, what would be the EMF for the following cell? Well, first thing, of course, we'd need to come up with to get the potential for the cell is we'd need epsilon 0. So we'd have to go to our table of reduction potentials and look up zinc and thallium. The bad news, of course, is that thallium isn't on our table. So now what? Well, now we're going to have to answer the question using the information we already have, which is the equilibrium constant. And so the question becomes, what is the relationship between the equilibrium constant for a reaction and its cell potential? That brings us back to our friend the Nernst equation. The potential for the cell is the epsilon 0 minus 0.591 volts divided by n log Q. At equilibrium, the cell potential, of course, is 0. So epsilon 0 minus 0.0591 n divided by n, log K. So log K is the epsilon 0 multiplied by n divided by 0.0591 volts. Well, we were told the equilibrium constant, 1.6 times 10 to the 14th. So the log of 1.6 times 10 to the minus 14th equals epsilon times 2. It's a 2 electron transfer divided by 0.0591. And therefore we find the E0 for that cell is 0.41973, or in other words, 0.42 volts. Now we can go back and put that potential into our Nernst equation. 0.042 volts minus 0.0591 volts divided by 2 log of the concentrations. The thallium ions and the zinc metal are the reactants, so their concentrations go on the bottom. The thallium metal and the zinc ions are the products, so their concentrations go on top. The thallium concentrations have to be squared. The concentrations of the metals are, of course, 1. And we have to put in the zinc ions and the thallium ions concentration. And we find out that they end up being 5,000. The log of 5,000, 3.7, times all that gives us 0.109. And, of course, it's a positive number because we have more products than reactants at this point, so the potential should be going down. And we end up with the potential for the cell as 0.31 volts. If instead the question had asked for the delta G of this rather than the cell potential, what would you do? Well, delta G is related to cell potential by minus NF epsilon. So, minus, it's 2 electron transfer, 96,485 coulombs per Faraday. The potential at this cell is moment is 0.31 volts. So 59,820.7 volt coulombs. A volt coulomb, of course, is 1 joule of work. So the delta G for this react cell at this point is minus 59.8 kilojoules. And this is the kind of interrelated question that you're going to face on the AP exam. So what other things do we run into as far as voltaic cells go? Well, let's consider some other possibilities. If we have the following cell, what would the cell potential be? Well, we're going to have to look up the potentials for the zinc ions and lead ions and see which way the electrons are actually running. Reduction potential for the zinc ions, minus 0.76 volts. For the lead ions, minus 1.3 volts. The lead's the more positive potential, so it's going to run as written. And so the zinc's going to have to be running backwards. So our reactants are the lead ions and the zinc metal. The products are the lead metal and zinc ions. The potential for the cell, the minus 1.3 volts for the lead's reduction, and for the zinc's oxidation, minus 0.76 volts. But since that's running backwards, we change the sign. And so we find the potential for the cell would be 0.63 volts. And left to its own device, the electrons would be moving from the zinc anode over to the lead cathode, and the reaction would run from there. That's the spontaneous direction. Does it always have to run that way? Well, no. We can make it run the other way. We could, for example, put in an electric dynamo and push the current in the opposite directions. That is, we could provide a potential that would drive the reaction in its non-spontaneous direction. Doing so is what is known as electrolysis. In an electrolytic cell, you are using an outside potential to drive the reaction in the cell in a non-spontaneous direction. That is, you're making the current flow in a direction that the cell would not do by itself. Which does, of course, bring us to current. What is an electric current? An electric current is flow of charge. It's an amount of charge being transferred divided by time. So what kind of units do we have for current? Well, we have the official unit for charge, of course, is 1 coulomb. And our official unit for time is 1 second. So when 1 coulomb is transferred for over 1 second, you have a 1 ampere current. Or in other words, a 1 ampere current flowing for 1 second transfers 1 coulomb of charge. So how many electrons are getting transferred when we run our current? So how many electrons would be transferred if a 5 ampere current ran for 5 minutes? Well, our 5 ampere current is 5 coulombs per second times 5 minutes times 60 seconds per minute. We'd be transferring 1,500 coulombs of charge. 1,500 coulombs times 1 Faraday. A Faraday is 96,485 coulombs of charge. So we would be transferring 1.55 times 10 to the minus second Faradays. And a Faraday, of course, is a mole of electrons. So we would have transferred 1.55 times 10 to the minus second moles of electrons. So we're transferring electrons when we're running our current. Well, adding electrons to something is reduction. And so we can ask questions like, how many grams of silver metal can get plated out at the cathode of our cell if we are running a 7.5 amp current for 10 minutes? Well, how much of this do you get if you use that? It's stoichiometry. And the first step in any stoichiometry problem is balance the equation. Silver ions in solution are gaining electrons. They're being reduced to silver atoms. And so, 1 electron reduces 1 silver ion to 1 silver atom. So how many electrons are we transferring? Well, 7.5 coulombs per second times 10 minutes times 60 seconds a minute will have transferred 4,500 coulombs of charge. 4,500 coulombs of charge times 1 Faraday is 96,485 coulombs. We get us Faradays. We get 1 mole of silver metal for each Faraday. That's our mole ratio. And finally, of course, 107.9 grams per mole of silver we would be able to plate out 5.03 grams of silver. And this is an important point. Electrolysis is just stoichiometry. It's just stoichiometry with electrons rather than atoms and molecules. We're transferring the electrons. We're looking basically at only half the reaction going on in the cell. But a Faraday is a mole of electrons. And so it's a stoichiometry like any other stoichiometry. You have to go to moles. It's just that you're going to moles of electrons. That is, you're going to Faradays. And you are getting the amounts not with grams or concentration, but rather with current and time. And so there's nothing else special about electrolysis. It's just stoichiometry with Faradays rather than moles of reactant. So, how long would it take an 8 amp current to plate out 1.5 grams of chromium from an aqueous chromium chloride solution? How much of this do you need to do that? It's stoichiometry. And the first step in any stoichiometry reaction, of course, is balance the equation. The chromium-3 is ions in solution. You are adding electrons to it to change it into chromium metal. It takes 3 electrons to reduce the chromium ions to chromium metal. Next step, go to moles. 1.5 grams of chromium times 1 mole per 52 grams of chromium gets us moles of chromium. 1 mole of chromium reacts with 3 Faradays. That's our mole ratio. So we're going to need 0.08654 Faradays to run the reaction. A Faraday is 96,485 coulombs. So we're going to need 8,349.7 coulombs of charge. The current is coming at 8 coulombs per second. So it's going to take 1,000.04 seconds, or in other words, 17.4 minutes to plate out the chromium from the chromium solution. Which brings us to the final topics in Chapter 18, which are batteries and corrosion. A battery, of course, is simply an enclosed cell, where one end is the cathode and the other end is the anode. The first really commercial was, of course, what is known as a dry cell. When you moved on from there, they now use more advanced combinations and get more power and longer life out of other things, and so we talk about alkaline batteries instead. But it's simply a way of changing chemical energy into electrical energy in your hand, rather than having to have all the other elaborate stuff. As far as corrosion goes, oxygen has a much higher reduction potential than almost all the metals. So you'd expect any metal exposed to the atmosphere and the oxygen would quickly become some kind of metal oxide and be useless as a piece of metal. The good news is the kinetics of that reaction does tend to be somewhat slow, and so metals can in fact be used in the atmosphere. On the other hand, some of them, specifically aluminum, have this reaction take place very quickly, but it ends up forming a layer of aluminum oxide on the surface, which is basically inert, and protects the metal underneath from further attack by the oxygen. And so, even though aluminum has a really high potential, it ends up being very unreactive in the atmosphere due to this layer of oxide. Iron does something similar. The problem is the iron oxides that are formed tend to be somewhat soluble in water. So when iron, or steel, that is repeatedly wet, these things tend to dissolve. It improves the rate of attack on the oxygen on the metal, and therefore we get corrosion. A simple piece of iron or steel that is wet tends to rust much faster than it would by itself. To protect iron pipes and steel, we often add another metal that is even more reactive than the iron, and it becomes that metal that gets sacrificed rather than the iron. That's known as using a sacrificial anode. And that basically brings us to the end of Chapter 18. in our discussion of electrolytic cells.